and I'm currently working as geotechnical support engineer in the Optum Computational Engineering. So it's a pleasure to welcome you all on the today's webinar on titled Design of Shallow Foundations, Limit Analysis Approach. And throughout the session, if you have any questions, please feel free to post them in the Q&A chat box. We'll be happy to address them either during the discussion or in the dedicated Q&A at the end. You may also reach us via email if you have after the session, if you have any further queries. So I'll quickly jump into the session. So So this is the session overview. I, along with my colleague, Dr. Ankita Dhar, together will taking you through the session overview. I will cover the introduction and the overview of Optum GX capabilities. And she will cover the fundamentals of shallow foundations and reviewing the bearing capacity theories and the settlement analysis and the design approaches from the theory to practice, including the codal provisions, and should go through the numerical modeling using the limit analysis approach for geotechnical problems related to the foundations. And at the end, we have a dedicated Q&A, as I already mentioned. So who we are. Before we get into the main topic on shallow foundations, let's take a moment to cover the company's overview. So just a quick setup before the real action begins. Optum Computational Engineering develops the advanced and user-friendly software for the design of geotechnical and concrete structures. And Optum Computational Engineering is founded in 2010 in Copenhagen, and it's a Denmark-based firm. So our global outreach extends over 50 countries and over 400 universities and 80 industries worldwide. And our first branch opened in Gurugram in India in 2024. So about Optum GX, today, as I mentioned, we have two divisions. One is in the structural and one is in the geotechnical. Today, we are discussing about the software Optum GX, which is purely geotechnical related thing. So earlier we have Z2 and G3. G2 is capable to model the plane strain models, which are 2D models, and G3 is dedicated for the 3D. So based on the market requirement, we come up with the new software by merging the 2D and the 3D in the single user interface. So which is named as Optum GX. So the Optum softwares will work based on the functionality of finite element method plus limit analysis. So this thing Ankita will discuss in the further in detail. And as I mentioned, integrated 2D and 3D in the single FEM workspace. And in the Optum, we have our dedicated analysis capabilities, which are used to calculate or model complex geotechnical problems related to sea pace, factor of safety, slope stability, and deformation. So different kind of individual analysis capabilities are there. So this makes the Optum calculations are better with faster convergence. And in Optum GX, the geometry modeling is very simple. If you have your DXF file, which made in the AutoCAD, so you can easily import to create the modeling and it will create in fraction of seconds. And all the modeling tools we have like line, point, cone, rectangle, extrude, revolve, just like the similar CAD modeling software. CAD modeling tools are available. So those who are more familiar in their design firms or in the academicians who are more familiar with the CAD, they can easily create any kind of model which is useful for the geotechnical analysis. And based on the modern trending, so Python plays a key role in making the things quicker. So we have our dedicated Python inbuilt feature is there, which makes the users to prepare their own modules and models. And there is a detailed post processing visualization will be there. So this is the workflow. For a software, we need to convey that what is the geometry, what is the cross section, and what kind of a properties. So software is like a black box. We need to feed. The user should know the basics, how to do and what to do. So in that thing, Optum GX plays a key role because the things are very easy and very simple. And how easy and how simple, I'll let you know. See in the geometry, if you have DXF, you can import. If you want to prepare any kind of material, You can create, you can extrude from 2D to 3D, and you can slice from 3D to 2D. And we have vast material library, including more Coulomb material model, means C5 model. And we have Hook and Brown for rocks, Tresca, and modified cam clay, Drecker Sprague. There are different kind of material models are available. And the features, the user can give the boundary conditions, like just like if you have a 3D X, Y, Z fixed in all the directions, like fixed support. If it is fixed in one direction and free in other direction, like free support you can give. And coming to loads, you can give the fixed load at point or at the corresponding line or surface load. The movements also you can give similarly. And the mesh refinement, if there is a soil body is there within the body, if the user want to give localized mesh at the corresponding location where it is more precious or something, he can give the localized mesh. And structural elements, like in the particular in the geotech, if the user want to do the ground improvement in terms of like to safeguard the slope against the sliding or landslides will be there, right? There they can give the soil nailing, and pile elements are there we have. And the geogrids like geosynthetics are also possible to model within the software. And in the fourth stage manager means the user can do n number of analysis in the single file by cloning the analysis. Means clone is nothing but copy. And he can add different stages, like stage one, like excavation, stage one, stage two, stage three, he can do, means the user can do. And one more thing is that you can add any kind of 2D and 3D in the same. And in the mesh, if the user is very interested to define the coarser or finer, he can give coarser or finer, very finer. No, the user is very much interested to give his user defined mesh. The user can give with a number of elements like 1000, 2000, 10,000. And there's a mesh adaptivity. This I'll discuss in the further slide, how the software algorithm will decide the finer mesh where the requirement will be. And in the solving, we have dedicated analysis for individual analysis for calculation of CPAs, factor of safety and all. And once you have completed from the geometry to the analysis, so the user is interested in the post processing, how the results are, how the animation, what kind of a results he require. And after that, in the report generation, the user can simply export the corresponding results, what they require, and it can be generated in the PDF format in less than a minute. So how Optum GX is different? And so the user should know when to go for the 2D and when to go for the 3D. If you have infinite in the outward direction, you can simply cut that cross section and you can make the 2D analysis. Suppose if I extrude this, the loading will be like strip with the infinite. And suppose the user want to do, suppose foundations, if you take, if there is a square footing or rectangular footing, there is a localized load at the corresponding location, which cannot be done in the 2D. So the user need to go to the 3D. And the second thing is that modeling 3D is complex compared to 2D. If the user is very familiar with the modeling, for him, it is fine. Those who are very new to the modeling, for them, it will be complex. So for that Optum, how it makes easy. So once the user has prepared the 2D model, he can simply convert the 2D into 3D in a single click. Means there is an extrude option is there. If you have the 2D geometry, just click in the extrude with in the outward direction, Z direction, and you will get the corresponding 3D geometry. And if the user is interested to convert his 3D models to 2D, there's a slicing technique is there. Simply he can slice at the corresponding section and it will convert into 3D. It's just a swap 2D to 3D and 3D to 2D. And see, there is a small video clip, so it will be easy for the users to visualize how the 2D to 3D. See how plane strain models are converting from 2D to 3D. This is how the things will be very easy once you switch into the software. Um, so this is how the 2D models are converting into 3D. So adaptive meshing. What is meant by adaptive meshing? So see here in the picture, there is a footing which is resting on the foundation soil. After that, the soil domain is discretized into number of elements, and at certain regions, it is discretized into very finer. So what is meant by this adaptivity? Mesh adaptivity means the software continually refines and adjusts the finite element mesh in the critical, means in the critical areas or zones with steeper stress gradients or complex geometry or evolving failure mechanism. This is the failure envelope, right? Terjagi's in the, if you know about the Terjagi's failure mechanism means, and this way the user gets more refined elements where it matters, and vice versa, the coarser elements where it does not require. So what it makes, it minimize the unnecessary computational time and enhances the accuracy, and it leads to the better convergence. And coming to the next. So as I mentioned, there is a customization with Python. This is a small clip the users can see, and parallelly I'll say few words. And with Python, the users can easily script their own geometry. Suppose if the users are more, their day-to-day work is particular to certain thing, or they want to do different kind of parametric analysis, just like changing the slopes or changing the heights and all, the user can make his own geometry by making the Python plugin. And it will, what it will do, it will automate the repetitive tasks, decrease the computational time, and enhance the efficiency. Suppose in any firm, there are, if the, say, if the designers already prepared some Python plugin, I mean Python module. So the young engineers who joined recently, they can directly use this as a base to do their things very quickly. So, and these are the analysis capabilities, how Optum do the things quickly with better convergence, because Optum GX has the individual analysis to do the corresponding problem requirement, geotechnical problem requirement. The first, like in situ stress, we have the in situ stress, which is used for calculating the K-naught procedure, just like in situ stress means K-naught procedure. And if the user want to do particularly seepage and transient, means user is interested in the saturation, pore water pressure contours, or hydraulic heads. So the user can go with the seepage analysis. Suppose the user want to determine the ultimate collapse state, so he can switch on to the load multiplier analysis. In the deformation analysis, like consolidation, time dependence, and elastoplastic. So load deformation analysis, what does it mean? It determines the stress and the displacements caused by applied load increment on the soil, just like a pre-described settlement and all. And factor of safety, and Optum is determining the factor of safety based on the strength reduction method. Suppose if the user wants the Moore Coulomb model, using the Moore Coulomb model for his geometry, so it will capture the C and phi, which plays a key role in assessing the factor of safety. So until the failure occurs, means the shear strength parameter tend to reduce. Suppose if you're using hook and drawn, so in that the sigma CA, uniaxial compression strength, and material constant MI, they will place a key role in the strength reduction method. Suppose if the user is interested in doing suppose assessing the dam's slope stability along with the seepage. So he may choose the factor of safety, because the seepage analysis is already imported within the factor of safety. First, the seepage will work, and then corresponding factor of safety will be determined. And in the mesh, so it is basically to visualize how the things will be visualized clearly. Means once you prepared your geometry here in the picture, and how the geometry is discretizing, so the user will visualize. In the practical application, how Optum GX plays a key role in solving the complex geotechnical problems in different domains in the geotechnical industry. So Optum GX is capable to model and deliver things related to slope stability analysis to determine the corresponding factor of safeties, and the shallow foundation to determine the bearing capacities, to assess the deformations. And in the retaining walls, just like this is the MSC wall, mechanically stabilized earth wall, or retaining walls, how they deform laterally deformations, and how the factor of safeties are there. And dams and embankments, if there is a overhead reservoir is there, how the seepages. Along with that, the user may see the factor of safety, also the deformations, and the braced excavations, how the plate elements, if you are giving the excavation with some bracing support, and how it is deforming. And we are capable to the tunnel also. And I'm winding my presentation, and thank you all for your attention. And I'll now hand over the session to my colleague, Dr. Ankita Dar, to continue with the next part. Thank you.
Okay. Thank you, Dr. Avinash. It was Thank you for explaining about the Optum GX briefly, and it was a wonderful explanation. Now I would like to talk about the topic of today's presentation, that is design of shallow foundations, limit analysis approach. I hope I'm audible and visible to you, like my video and audio is working fine.
Yes, it's absolutely clear.
Okay, thank you so much. So, hello everybody. I am Dr. Ankita Dhar and I have completed my PhD from IIT Bombay and I work as geotechnical support engineer at Optum CE India. So today we will discuss a little bit about shallow foundation design. I know this is a very basic topic, but to understand a basics about a new topic, I think it is a very good topic to start with. So as everybody is from geotechnical fraternity, I'm sure you know about shallow foundation, but just to give you a brief start, we would like to start with the shallow foundations. And what is it? It's a foundation where the depth of footing is less than the width of footing. So why we provide shallow foundation? Because we have a strong soil strata. So whenever there is a strong strata, we can go for shallow foundation and it transfers structural load at very relatively smaller depth. Okay, so there are different types of shallow footings that can be provided. So if we have a single column load transferring to a single footing, we call it isolated footing. But say there are two footings which are very close to each other and their boundaries are overlapping, we can go for combined footing as well. And there may arise a situation where we can't increase the size of the footing, say due to the property line or due to some reasons. Then we can also provide a strap between the two footings to transfer load from one footing to another. Then if the situation that we came with the combined footing comes a lot, like in a whole larger area, we can go for raft footing where all the footings are overlapping and the loads are high. So we can provide a big raft through which load can transfer to the larger area. And then there are also strip footings basically for load bearing walls. So if there is a continuous load throughout the length of the footing, so we provide strip footing there. Okay. So we all know like how structure interaction happens. So it mainly happens through few of the things. First is when the load gets transferred to a footing, it get dispersed at a wider area. So at an angle of dispersion, it may spread. So we have to take care of this angle of dispersion because there may be mutual interference of the footing. So say if there are closely spaced footings, there may be the mutual interference of the dispersed area at which the load is transferring and which may cause increase in the settlement and reduction in the failure pattern. So we have to take care of such things. There is also contact pressure that develops due to the footing. So depending on the type of footing and the type of strata, there could be different types of behavior that may generate. So for example, if there is a rigid footing, so there will be uniform settlement throughout the base of the soil. But if the strata on which the load is getting transferred is clay, then you will see that the stresses are more at the edges and lesser at the center. Similarly, if there is rigid footing with uniform settlements on the soil and the strata is sand, then there will be more stresses development at the center and lesser at the edges. But for flexible footing, this settlement is not uniform. The footing display will settle non-uniformly, but the contact pressure that develops will become uniform because of that. So the way in which the flexible footing settles will differ for clay and sand, but the contact pressure that gets developed beneath the flexible footing will be uniform. So there is also a mutual interaction between the soil and the structure. So when structure imposes load on the soil may deform. But if there is, say, differential settlement, there may be, due to those differential settlements, the loads may increase in the structure, which will affect the performance of the structure. And since loads are increasing and it is affecting the performance of the structure, it will impose more loads on the soil. So this way, soil and structure interaction is also mutual. So next, coming to the modes of failure on how, when we apply loads on the foundation, how they are going to fail. So there could be general shear failure, local shear failure, and punching shear failure. We all know about that, but I would like to explain it with the Optum GX software. So we say that when we have a dense sand or dense soil, there will be a general shear failure. So if you look at the properties of this material, so this is the soil, uh, and this is the rigid footing over it with the ultimate load. Load multiplier means that ultimate loads will be acting on it. So, and I have taken the phi value as 38. So if you look at the failure plane, you will see that it is following proper Terzaghi's bearing failure. And you see it is very wide in the range. So it is still here. Similarly, if you go for punching local shear failure, you will see the similar failure pattern. But now, because the soil, if you go to the soil, you'll see the soil, the phi value here is 25, which is loose soil. So here it has narrowed down. If you compare it with general, see how broad this failure plane was. And for local shear, it will narrow down. And then for punching shear failure, which will occur in very soft clays. So here, if you look at the material, I've taken Cu as 20. Okay, so undrained shear strength, I've taken 20. There's soft clay. So you'll see it is punching into the soil. So this is the punching shear failure, which will occur. Okay. So these are the different types of failure that may occur in the soil. And there will be a vertical settlement with the nucleus slip in punching shear failure. Then coming to the theories. So there are a lot of theories that are available. Terzaghi's bearing capacity theory being very commonly known. So he developed an analytical method to determine the ultimate bearing capacity. And these are the assumptions that it is a shallow footing, it is a continuous strip footing. So it is a standard 2D problem of plane strain condition. And it is homogeneous, soil is homogeneous and isotropic, and the load applied are vertical. So from here we get, from the Terzaghi's analysis, we get the equation that there are three zones that get formed. So there is a triangular zone, then there is a radial shear zone that forms. And then at the end, there is the formation of the Rankine's passive zone, in which you can say that CE act as a wall that gets uh, pushed into the soil. So this is the Rankine's passive zone. So the equation that Terzaghi gave is CNC plus gamma dNq plus 0.5 gamma B into N gamma. And these are all the bearing capacity failures. Now, when we have to design a foundation, so based on Indian standard codes, we have to take care of two basic criteria. First is shear criteria, and another one is the settlement criteria. So according to shear criteria, the foundation should be designed such that it does not fail in shear. So whatever, it should not reach here. The loads should not reach here in this zone. Another is the settlement criteria. So the settlement criteria states that the settlement corresponding to the load. So if we have applied this much load into our soil, these are the dead load and the live loads, all the loads that are going to act in the footing. If this is the load, then the settlement that we are getting corresponding to it should be within the permissible limits. And we get those permissible limits from IS 1904. And we can calculate settlement using IS 8009, part 1. I'll show you. These are the pages from the IS code. So according to IS 6403, you can see this is for the general shear failure, and this is the local shear failure. So there are several shape factors, depth factors, inclination factors, and water table correction factors for both general and shear. And this is the settlement criteria. So for immediate settlement, we have to check the equations as per IS 8009. And then like if the settlement is within permissible limit, we will get it from IS 1904. And these are the limits that have been given there. So like if we have reinforced concrete structure, it should be 50 mm if it is in sand. Now, these are the basic, like how we will do it with IS code provisions. Okay. Now, coming to the limit analysis. And before jumping into the limit analysis, I first want to explain you the history, like where it comes from. And it is not a new concept. It is actually a very old concept. Limit analysis is derived from from 18th and 17th century concepts of maxima and minima. So these were developed by Newton, Euler, Lagrange, Leibniz. So they developed these maxima and minima, and then further using those in 19th century, plasticity theory in materials were developed by Tresca and von Mises. So they formulated yield criteria based on maxima, minima, and plasticity theory. Then the limit theorems in plasticity were developed by Drucker and Prager in 1930s and 1950s, and they used these theorems to develop limit analysis theories. Then in 20th century, again, when these were developed, they were widely accepted and used in structural engineering. So to estimate the collapse load, of beams, frames, slabs, limit analysis is used. Then during the same time, Terzaghi developed the bearing capacity theory that we discussed a few minutes back. Okay. And then the limit analysis was used to extend the problem. So the Hansen gave us the shape factors. So they are all based on limit analysis only. And then with the advancement in the computational tools, now we have finite element and limit analysis tools that can use this limit analysis theory in practice in geotechnical engineering. So this was the history of limit analysis, but what it actually means. So limit analysis, in using limit analysis, we can determine ultimate load, but we do not consider the entire load deformation history. So usually in geotechnical engineering, whenever we are talking about the ultimate load, we go for load settlement analysis. We put some load on the soil and we check the settlement. And when it reaches the ultimate load, it converges. That's when we call it as the ultimate load carrying capacity. But using limit analysis, we can calculate that ultimate load, without going through the entire load deformation history. Okay, so there are two bounds that we get. So we get a lower bound value and an upper bound value. So what lower bound value does is it satisfies equilibrium and does not violate the yield criteria. So when I'm saying equilibrium, I mean equilibrium of forces. That means the loads that are acting on it are getting the equal reaction from it, and soil is not yielding. So the moment our first yield point we get, that is when lower bound works. Okay. Then upper bound means that it satisfies compatibility and yield criteria. It is based on kinematic admissibility. Okay. So the loads that we get from lower bound are relatively safer loads and below true collapse load. And the values that we get from upper bound may exceed the actual collapse load. And when we get the both lower bound and upper bound values together, like if you're getting the same results from upper bound and lower bound, that is going to be our exact solution to a problem. Now, I would like to compare limit analysis software with the displacement-based finite element softwares. So if you go for any finite element-based software, they work on kinematic part of the governing equation. That is the same as the upper bound value, that upper bound equation that I explained. Okay. So what they do, they go for load displacement. So as I was telling, you calculate load and displacements, and when the result starts converging, that is considered our exact load. So this is the exact solution. For the same solution, it will take the load deformation history, and based on the mesh, we will reach some value that may not be very close to the result. So what we do, we increases the mesh density and we reduces the mesh size and try to reach as close as possible to the exact solution. This can help you explain. So this was our first iteration. And then when going for mesh convergence, like trying to refine mesh as possible, we are reaching closer to the solution. But this is our exact solution, which we don't have. We don't know if this green line exists or not. It may exist here or it could be here. We don't have any idea where it is, but our results have converged and it is closer to the exact solution. That is what we assume. But coming to the limit analysis, now we have some exact solution. Okay. So if you look at this blue line, this will give you the lower bound. And if you look this red line, this will give you the upper bound. So lower bound equation, again, static part, it will consider equilibrium and yield, and upper bound will consider stress, strain, and flow rule. Okay. So same now, if we are here, we can refine our meshes and reach closer to the exact solution. Now, what is different here is earlier we did not know how far we are from the exact solution. when we are only considering the kinematic part. But because we have lower bound, now we have some range bound. Because of the bounds, we know where we lie. Even when our exact solution is this and we are at this range, we know how far we are from the exact solution. So this way, limit analysis helps us choose a better reliable results. So when our upper bound value and lower bound value converges to a value that is very close, we know that this is going to be the exact solution to our problem. So this is how, this is the basic theory of the limit analysis. I hope it is clear. Now, using these theory of upper bound and lower bound and limit analysis, how we can design the same foundation that we were designing using the equations from the Indian standard codes to the Optum GX software. So basically, as I told you, there are two criteria. There is shear criteria and there is settlement criteria. So for shear criteria, we have an analysis called load multiplier analysis. And for deformation criteria, for settlement criteria, we have an analysis called deformation analysis. I'll show you in Optum GX. So, okay, this animation is still running. Just give me a second. I'll just move it. So when I say limit analysis, as you can see, this is the main screen that pops up when you're working with on Optum GX. So designing is also very easy. I have the models, but I would like to show you how to make one. So basically, you can create a simple geometry like so. So this is a rectangle. And then I want to create a foundation here. Then I'll use this. Okay, and I can, so my geometry is created. Now I can assign material to these. So I'll add solid and I'll apply rigid to the foundation, to the footing, and I'll apply any more Coulomb basic model to the soil. And now I have to also assign some fixities. So I'll go for standard, and this is how fixities have been assigned. Okay. I can also, now when I'm talking about the load multiplier analysis, my main aim is to determine the ultimate collapse load. So for that, in this foundation, in this footing, I will apply a load called multiplier surface load. So I hope you can see this is the multiplier surface load. Okay. So I'll apply this multiplier surface load. Okay. So this is, it will keep on increasing the load until the collapse occurs. And here you can see it is -1 kilonewton. So the multiplier value that we get, we multiply it with this and we can get our multiplier load. And then I have to choose the analysis. So here in Optum, we don't have a single analysis. We have different analysis for different problems. So if we are just going creating a mesh, we can go for mesh analysis. And if we are going for C page problem, we can go for C page. And then right now our focus is on load multiplier analysis, as that is going to give us the ultimate collapse load. So we'll go for load multiplier analysis and click on this run. Okay, run analysis. So when I click, within 1 second, you see I have already gotten my result, and my load multiplier is 676 here. Okay. So these result, this is the run log, and you can see the result here at the bottom. I hope this is clear. So this way we can calculate. So in this way we can calculate the shear criteria, like the ultimate collapse load that we were getting from the IS 6403. Now, another value that we wanted for the same model is for the deformation analysis. Now, for deformation analysis, I'll just clone this model. Cloning is just using the same model, but changing few properties. I want to change few things. So I'll just clone it. So here we have this option. This you see, this is for cloning the material. Okay. So I'll just clone it. And now you see my another model is created. Now, you know that for deformation analysis, the load is fixed. We know what load we are going to apply. So we can't use multiplier load for that. So we have to change the load that we are applying. So we'll use I'll click on the same edge that where I had applied multiplier load. And from here, multiplier surface load, I will change it to fixed. And let's say 200 kP is acting on it. So I'll change it to 200. And I can run the analysis and I'll know what are the deformation corresponding to the what are the corresponding to the load. Sorry, I have taken load multiplier. So I have to change the analysis to deformation. Earlier it was load multiplier. Now for second problem, because this is fixed load, we have to go for deformation analysis. And I'll run the model and you can see I'll get some value of deformation corresponding to the 200 kPa that I have applied. And so I'm getting 26 mm. So that is, then I can compare the value from the codal provision and use those values. So this way we can go for load multiplier analysis and deformation analysis as given from the code, like corresponding to the codal provision. Okay. So this is again the results from shear criteria. So you can get the load multiplier for shear criteria, failure criteria, and for settlement criteria, you have to check the values from here. Say ours, in our case, if it is reinforced concrete structure, so settlement should be maximum 50 mm. And the model that I already run, it is giving 43 mm. So it is within the limits. So I can go with this footing size that I have chosen. These are the results that I have shown. Okay. So this is the load multiplier 1210, and this is for the same soil deformation analysis and the maximum displacement that we are getting. Now, these were the basic how we can just convert our IS results like to the settlement and shear criteria. Now coming to the very basic examples that we have studied in our books. So I have taken a simple theoretical example from Principles of Foundation Engineering by BM Das. So they have designed us, so they have asked us to use a square foundation, 2 meter by 2 meter in plan. And these are the properties, and we have to determine the value at which ultimate shear failure occurs. Okay. So what we will do, we'll design the same. So I have already done that. I'll show you how to do this. But if you look at the square footing, it is a pure 3D problem. You cannot convert it into axisymmetry or plane strain. So when you are designing a square footing or of any irregular shape, you have to go for 3D modeling. So here you can, as Dr. Avinash told you, you can obviously convert your models from 2D to 3D. But for such problems, you can directly start at 3D. So here you see this option of 3D here. So you can click on this and then you can choose this create box option and you can create the soil domain. It's very easy. You just have to give, if you have the domain points, you can give it and you can choose the height. So this way you can create your soil domain. And again, now I have to create a square footing. So even though it is not symmetric from 2D to 2D perspective, it still has a quarter symmetry. So this is a simpler problem, but if you have a very big problem and you can convert it into smaller problem, you should always go for that. So here, instead of going for full model, I will go for quarter symmetric model and create a, so 2 by 2 will become 1 by 1. So I'll go for 1 meter by 1 meter, 1 meter by 1 meter. And then I have to give a height. I'll go for 0.5. And this way I can create a footing very easily. Now, next step is to assign material. You can assign the material that is from the materials tab and give all the properties that you want. And you can also go for rigid. So this way I have created this problem model. Okay. Now, if you look at this model from BM Das example, there is loads on the footing and on the soil as well. So the soil, the loads that are on the soil are actually overburden loads that are going to act at the level of footing. So you can see the value from here. And the value, and this load is the multiplier load that will give me ultimate collapse load. So we can do that here as well. What I'll do, so if you look at the bottom, all of these selection points, these are all checked. Okay. So what I will do, I will uncheck this one. Okay. So I'll uncheck volume. So now I can select all the faces. And if I check the volume, I can only select the volumes. So I'll click here and I will select the face. This is the area where I want to provide surface load. So then I'll go to add features go to load and select multiplier surface load, and the value will be -1. I can change it to if I have any other factor, but right now I'll go for -1. And to provide this overburden pressure, I'll just click here on the face and I will add features as fixed surface load. And the value will be very less depending on the unit weight of the soil that is there and the depth of the footing. So here I had given somewhere like 24, so I can go for that. This way you can easily, very easily, within few seconds, create your 3D model. Okay. Now I already have analysis results here. So if you look at this footing, this is 1 meter and it is quarter of the footing. Okay. Now, if you look at the load multiplier, this is the value that we're getting for lower bound. Now, how do we change it to lower bound? So basically, when you go to this model, I'll go for load multiplier analysis. And if you look here, there is this element type as mixed. Okay. So from this mixed, we have to change it to lower. So I'll change it to lower. This will give me the lower bound result. I'll just change it to lower bound name. Okay. Now I'll clone this model and not change anything, no, any geometrical or features, nothing will change. Only from this element type from lower, I have to change it to upper. So this will give me the upper bound value. And as I told you, mixed will give you, like if you want to go for a quick analysis, which will give you value somewhere between upper and lower, you can go for mixed analysis. So third model, I'll go for mixed analysis. Okay. So this is mixed. So if I run these models, I'll get results as upper, lower, and mixed, and I'll show you the results here. So so these are the results from the book itself. So I have taken these results from the book. It's 137. And these are the limit analysis results that we have gotten. We have gone for upper bound and lower bound and mixed, and this is the analytical solution. And analytical solution is somewhere between upper and lower bound. I can go for higher refinements and reach very close to the result. But if you see, upper bound values are matching more with the analytical solution because these are based on the upper bound theories. Okay. Now we have also similarly we have also done verification with other models. So Cox have given this model and he has found the exact solution and the for the square footing, again the square footing. So it is 188 kPa. Now we have also created, now if you go for verification, we have to find the exact solution. Now we have created the same model using Optum GX. Okay. And we have gone for load deformation analysis and we have determined the load versus settlement curve. And if you see, these are the comparative results. So we have taken this validation problem for another FEM tool. And these are the results from the FEM tool. And this is the result from Optum GX. And this is the exact analytical solution. And you can see how it is matching closely with the analytical solution. Now, these are all the analytical solutions and how you would apply this and how you would report this value for your design. So basically, if you have some borehole data that you're getting, and from there you're getting some C value, some phi value. So if you're working traditionally, what you will do, you will create some Excel file like this, and you will put your formula for, say in this case, it is for local shear failure. Okay, so you'll use the equation given as per IS code. You'll use that equation and you'll put all the values of C, phi. If you look here, these are all the values. Okay, so right now shape factor, because it is strip footing, so shape factors are 1, 1, and then you have to use all the bearing capacity factors. And from there, you can determine the ultimate bearing capacity. Okay, oh, sorry, this is 33.77. Okay. Now, what you will do, you will use the same, exactly same problem and solve it using Optum GX. So what we will do, we will create a model like so. As I think I have already explained how to create this model. So instead of creating it again, I will just show you how we did this. So you'll create this model, and for this, you'll go for load multiplier analysis. First, we are going for upper bound, lower bound analysis. Then clone this model and go for upper bound analysis. This will give you two values. And if we go to results, you can see one thing you might notice in most of the models is this very fine mesh. Okay, so you see this really refined mesh. You might have noticed it here as well. In case of this, see. So what I have done is I have used adaptive meshing. So when I go here, adaptive meshing, Dr. Avinash has already explained. So basically, wherever there is concentration of shear strains, where shear energy is getting developed, so the mesh will get automatically refined in that area, and it will make coarser in the other area where we know failure is not going to take place. So how it helps? It basically helps by considering our model as fine as this. If we made whole model this fine, it will take a very long time to calculate the results. But just by refining the plastic area, we are getting better results with lesser, like convergence, we are reaching faster. So here what I have done, I have taken model element type lower, mesh I have taken fine, but I have applied mesh adaptivity to it. So this will give me very realistic result, like converged result that we want. Okay. Then I have gone for upper bound also. I have done the same thing. You can see this is the mesh and this is mesh adaptivity. I have kept it as yes. Yes. Okay. So you can go for the results. So for lower bound, I'm getting 323.48 and for upper bound, I'm getting 340. This is in kilonewton per meter square. Okay, if you look here, the results from lower bound, to compare it from there, you can see it is 34.4 tons per meter square, and from lower bound, it is 32.34 tons meter square. Now, if these are two different values, and I can't report it that way, and I don't know how far we are from the results. If you look, analytical result is 33.7. So it is very close. Upper and lower bound are very close. That means this is very close to the exact solution. So what I have done, I have taken mean of these two values, which is 33.19, and I have shown how much discrepancy is there in the result. So this way you can report your result and you know exactly how far you may be from the result. That is 2 plus minus 2.5%, which is very less. So this way, limit analysis can be used in your application. Now, you must be thinking that these are very simple problems and I can do them analytically. But in shallow foundations, it is not just this. There are a lot of different shapes, foundation shape and size. And you can extend these theories to all the project applications of geotechnical engineering. So that way, even though this is a very basic topic discussing about the limit analysis and how these bounds are helpful, you can go for designing with all the projects and understanding the limit analysis for geotechnical application. Now, coming to the conclusion, as I told you, you can use these limit analysis theory for safer and economical design. And as you saw, I had shown you a few runs that the computational effort, the time and energy that it takes for computation is very less. Because of the optimization, it reduces computational time a lot. So that will give you more time to think and do the critical thinking. And it will provide, because of these lower and upper bounds, it will give you a reliable solution. You will have a better, more confidence in what you are presenting, the values that you are presenting. You will feel more confident in that. So it will help you provide those reliable bounds and help you make a better decision making. So I think I would like to conclude from here and thank you so much. And if you have any questions, you can reach out to me at ad@optumc.com and lsa@optumc.com. And if you have any sales related query, you can reach out to Mr. Shekhar Sharma at ss@optumc.com. Thank you. And if you have any question, you can ask us now. I'll stop sharing my screen and you can ask question. And you can also post your question here at Open QA. So do you have any question? You can raise your hand and we can unmute you if you want.
Yes, sir. Yes, sir. Yes, yes. We have received a couple of questions from Yatish Naik and Vishwash Khatri, and parallelly we are answering we are
Okay.
providing the answers to the questions
Okay.
in the chat box, and there are two questions in the Q&A also,
Okay.
and we have responded them.
Okay. Thank
Um,
you. Thank you so much. So I hope you found this session
if still,
helpful.
yes, if
Uh,
still anyone has question, they can ask or they can type it in the Q&A session.
okay. So
So it will.
yes, we can simulate geogrid and geotextile below the footing. I'll just quickly show you, but we were planning to keep another webinar for these, but I'll show you. You can just use this line element. Okay, I'll share my screen first. I think I have not shared my screen. I'll just share my screen. So we'll keep another webinar for reinforced earth structures, but I hope you can see my screen.
Yes, it is
So
visible.
basically to model a geotextile, you can create a line in 2D and just right click on this and add features and go to structural and geogrid. If this is like too much, I can tell you one more time. There is another way to do this. So basically you click on this line and go to features tab, and there are a lot of features available here. So in structure, you can make it plate or geogrid, pile row, nail row, depending on what you want. So right now you want to create a geogrid, so you can do that. And you have to provide all the properties of the geogrid like yield, force, stiffness, axial stiffness, and then you can also provide the interface properties. Like here, if you look, there is plus and minus. So here it is going to be automatically like it will take the adjacent soil, but you can give the reduction factors that you want to give. Okay. So any other question?
Yes,
Okay.
regarding the pricing and all,
Please contact
please
Shekhar,
contact our
Mr.
sales team, Shekhar Sharma. There is a
We'll
mail.
share
You can share
we'll
the
share the email.
screen. You share the screen, Ankita. Email.
I'll,
Yeah, if you
I'll
have
share
any
mail.
questions, you can ask orally also.
Just raise hand and we'll unmute you. So these are the details of the contact person. You can contact ss@optumc.com. Shekhar Sharma, Mr. Shekhar Sharma.
Good question.
So we would like you to share a feedback form and all the presentation and the video once it get uploaded, and we'll share all these details with you. And if you have any other query, you can contact us in these email addresses.
Yes.
Okay.
Yes, Payal, can I model stratified soil? Yes, you can do the modeling. If you have different stratified soil, you can model it. That will be possible.
Yes.
And
You can just create lines and then you can provide different material with
yeah.
the soil anxious.
And I think there is a question from Venkata Abhishek Shakleshpur Ankita.
Okay.
Yeah, in the Q&A, if you have seen
Okay,
settlement
I'll
from
just
Optum. Yeah.
Q&A. Not able to find the question.
Q&A. Please go to the Q&A.
Yes. Dilate is the angle for shallow foundation. This you have answered. This one, na?
Yeah.
Thank you. Well, does the settlement for Optum? Huh.
Yes.
Actually, okay. So we have not compared. Yes, but you will get very close results. We have already done few validation problems, and yes, the settlements will compare. And flow rules, we have this option.
Yeah.
There is this option for non-associated flow rule, and you can give the dilatancy, and you can also give the dilatancy gap if required. I think we can conclude the session now. And
Yes,
thank you
yes,
so
there is,
much.
and there is one
Thank
more
you.
from Vishwash Khatri, any numerical on groundwater modeling that we'll cover in the upcoming session.
Yes.
Yes, it's
Okay.
possible. It's possible. It's possible.
Thank you so much for attending. I'm really grateful that all of you could attend the session, and I hope you found this session insightful. And we will be coming up with a lot more webinars and more complex topics. Then this was the first, so we wanted to keep it a little basic. And I hope you will join future webinars as well. We'll come up with very interesting topics soon. Thank you.
Thank you. Thank you, everyone.